a player and you're trying to dodge this thing, and you see it shooting you like that, well, you gotta dodge back and forth. That will be quite obnoxious. Hey YouTube, how you doing? So I've got another tutorial for you today. Have you ever been playing a game, or you're developing a game, and you want to track the position of the player? So you've got an enemy, say this red thing in the center of the screen, and he just shoots behind me. So this becomes solvable to a good player, where all you really need to do to avoid this is just keep holding one direction. If you ever cut back, you might get hit, but as you can see, I'm spamming as fast as I can. You can dodge him pretty efficiently or jump over his trail. So, how do you solve this? What you would do is you would lead the position the target's going to go. So, this yellow indicator we have, that's leading where I'm going to be. And I'll show you how to make that in this tutorial. So, first things first, let's take a look at the code. This is generic code that you can use on any object to track anything you want, really, as long as it has a constant acceleration and velocity and it's not like colliding with things. This will work flawlessly. If it is colliding with things, things might get a bit more advanced. I might make a tutorial on that in the future, but if you don't want to use Unity's physics prediction system, where you give it a number of iterations to run through and then sort of work things backwards from there, this is for you. So this code gets a bit complicated. I'm not going to type it all out, but I will go through it line by line with you. So I won't get too much into the details, but it's very important here that we put this all in a coroutine that runs at the end of the frame. Because if you do it in late update and your physics are running in, say, update, it's going to happen after the physics. But if your physics are running in late update and this is also running in late update, it may decide to run before the physics. And you'll get very wonky behavior with your predictions. It'll spaz out a lot. This happened a lot when I was testing it. It's not fun. Trust me, you don't want to do that. So, all we do is late update. We start the coroutine, wait till the end of frame, and then we actually do the calculations. To get the velocity, we get the current position, we subtract the previous position, and then we divide by the time it took from the previous frame to this frame. Very straightforward. And then we calculate our acceleration as the current velocity minus the previous velocity. The reason we factor in the time into the actual acceleration is because if we didn't, the previous velocity would lose all the information about the amount of time it took on the frame prior. So, let's say your current velocity has a length of 1. And this frame, in the full frame, it was, say, 0.02 milliseconds. Now, on the next frame, this is your velocity vector. Illustrate it like that. And this one is of magnitude 1.2. But in reality, you're not moving any faster. The only difference is this number changed. So the 0.02 actually took 0.03. So it's very important to essentially factor this amount of time into the velocity so you get the appropriate value to get a constant velocity. You don't want a constant time, you want a constant velocity. So that's what this code does. So we set the average velocity equal to the current velocity that we calculated, the average acceleration equal to the current one. The reason I left these like this is if you'd like to say average velocities over the last 5 frames, you could do it that way. You could use this, you change this to an array, and then you just loop through all the previous velocities, average them out, and you could calculate it the same way. We get the projectile position, and then very important, at the end, we set all the previous values. So the previous position, previous velocity, previous acceleration. Now this is just the kinematic equation, where we're just returning where the projectile, or where it's going to be after 1 second. So the kinematic equation is x at time index 0 plus v at time index 0 times t plus 1/2 the acceleration times t squared. So the current position, x0, plus the average velocity with the time factored back in, because we divided it by the time, so now we need to multiply that time back in. And the total time it's going to take is the total time we're estimating divided by the frame rate. And then we add in 0.5, 1/2, the average acceleration times, same thing, multiply the time back into that acceleration, and math.pow, the total amount of time factored in with the time squared. And then last but not least, I just moved the indicator so you can see where this is going to go. So let's compile that. Hop back into Unity, and let's see what it looks like. So this red ball I have over here, you can see, if I can line it up, you'll notice the drastic change. That's because there's no collision information factored in. If you want to factor that in, you can. But for now, we'll keep things simple. I'll leave that to a future video. So you can see the instant it bounces, it goes exactly where it's going to be 1 second later, and it tracks it the whole way down. Our player, as you can see, when I'm holding left, up, right, it predicts the location. But you might be thinking, Viper, is that actually where the predicted position is going to be? Well, let's see. Right now, he's just shooting where we were. We want him to shoot where we're going to be. So, let's hop into the enemy controller. I'm going to delete the old code and then walk through this new code. So, if you want to use a constant speed, you always want your projectiles to go the same speed, which is most games, I think. If you want a consistent player experience, you definitely want people to know how long it's going to be till they get hit. And they can do that with a constant speed. So, first things first, we track the amount of iterations, and then in our while loop, because this could theoretically go on forever, we just make sure it doesn't go over some number, and we break out early. So, we spawn a bullet. We have our check time equal to the base time. Right now, that's 0.15 milliseconds. We draw a line just so we can visualize what this looks like. We get the position of where we think the bullet is going to be on the next frame, or not on the next frame, after the appropriate check time. Draw a line to that, and then we get the distance from where we think the bullet's going to be and where we think the player is going to be. I'm using a distance of 2. You could easily do 1.5 or whatever accuracy you'd like. You could fiddle with this. But I've found anything smaller than this value, it reaches the max iterations and doesn't actually find the intersection point properly. So all that this loop does is does the same exact code over here, but it just iterates the total number and it iterates the time. And my time per check is 0.05 milliseconds. Again, you could fiddle with that if you'd like, but I've found that works really well for me. My max iterations here is 100. I don't want to do too much more than that, but depending on your frame rate, because this all runs in one frame. So depending on your frame rate and your iteration step count, you could want more. And then we just set the velocity of the bullet. The velocity is really only to get the direction, so we normalize it, and then we give it the speed. Now, if we don't want a constant speed, if we want our projectile to adjust for how far we are, and we want to hit our player after 1.2 seconds. Don't care how fast the bullet is, change how fast the bullet's going, but we want to hit them 1.2 seconds later. That's very easy. The only difference here is instead of iterating to predict the position, all you need to do is just manually calculate how fast you'd have to go to get there. So, same thing as above. Our target position is the projected position, that method that was written earlier. Spawn a bullet. We get the direction it's going to go, this v3 velocity, and we divide that by the time until the target, and that'll give us how fast we need to go every frame so that we hit it in the set amount of time. Last but not least, we shoot it. Let's compile. Head on back to Unity. Go into our enemy, which has our enemy control, and first we'll try it with a constant speed. So our speed is 30, and let's see how it looks. I will turn debugging on so you can see. And look at that. We're hitting the player perfectly every time. Spawn a bunch of them. Look at that. Perfect tracking. Now, you do get the problem here where it shoots under. That's because we didn't factor in any collision. We could save that for the future, but for now, for what we wanted to do, it's nailing us every time with a constant speed. And you can see if we go further away, it's going to lead a lot further and still hit us. Boom. Bam. Just like that. So now, if we don't want to use a constant speed, we want to adjust the speed, but hit us 1.2 seconds later. We'll see how that looks. Now that one flies at us, but sure enough, it hits us. The projected position is working perfectly, and we've successfully annoyed our players. If you were a player and you were trying to dodge this thing, and you see it shooting you like that, well, you gotta dodge back and forth. That will be quite obnoxious, but the other method of just spinning in a circle gets too easy, so it's definitely good to add a little bit of variance, maybe a special attack that will track your player to really make them have to use their brain, so to speak, to dodge. And that's all there is to it. Like I said, this can be very powerful, but also very frustrating to your player. Let's switch back to a constant speed. I pretty much can't dodge this thing at a certain distance ever, and at a certain speed. There's almost nothing I can do. So yeah, definitely be careful with this, but it's extremely easy. It's generic. You can put this object tracker on anything. It's on the bouncy ball. It's on the player. And feel free to use it in your games. All the code is linked down below. And if you liked the video, be sure to give it a like, comment, subscribe. Push that bell notification so you get notification of all new tutorials I put out. And thank you for watching. Thank our little helper for hanging out with us this whole time. And I'll see you next time. Take care.